Okay, let's continue. Last time we looked at integration by parts. We're going to continue with that. So that's, you guys, a problem to think about. But before we get into that, let's do actually a couple more examples. What's the formula for integration by parts? Yeah?
Integral of u dv equals uv minus integral of v du.
Right. So you have an integral like this, you can compute it like that. And how do you choose your u? Yeah? WAAAY. And what do these stand for? The L. Algebraic, right? Which basically means polynomials, trig, and exponentials. You choose u in this order, right? So u is chosen in that order. And last time we kind of ended the class talking about this integral here, e to the x. Did anyone actually try that? See what you'd have to do for this? Wouldn't do that one directly. Let's start out with another example. We'll get back to that. But what if it were x squared e to the x? How would you do that one? So basic rule doesn't apply, and substitution won't really help. And so what we can do is we can try integration by parts. And according to WAAAY, we have an algebraic expression and an exponential expression. This guy would get to be the u. So if you start by saying u equals x squared, your dv would be e to the x dx. Your du would be 2x dx. And your v would be e to the x. And then you plug into that formula. U times v minus the integral of v du. So 2 here comes out, and we did with that. Well, how would you do this integral? It's integration by parts again. We again have a product of the algebraic and that guy, so we'll do another one. So here we set u equals x. Your du would be dx. You set your dv equals e to the x dx. Your v would be e to the x. And so pretty much you are going to plug in another version of the integration by parts. U times v minus the integral of v du. And so finally, that one we should be able to do. Integral of e to the x is just e to the x plus c. So we would have x squared e to the x minus 2x e to the x plus 2 e to the x plus c. That would be the answer. So given that we just did that, can you kind of see how we do this one? Yeah? You'd have to do that 5 times. Pretty annoying. We're not going to do that. I'm going to show you a way to do this using integration by parts, but a more streamlined version where you don't have to have like 5 sets of nested parentheses and taking forever to do a problem. But if you're brute forcing using this formula, this is what it might entail. You might have to do integration by parts several times. As we saw last time, you have examples where you might start out a problem with integration by parts, but you end up having to do a substitution. So again, once you learn techniques, you can mix and match them. And you kind of start out by trying to apply the easiest technique first, see what you end up with, and then if you have to apply another technique, you reassess as you move on. but that's basically the idea. Let's look at another issue. So here, obviously this guy brings up the issue of sometimes you have to apply integration by parts a bunch of times in a row, which in and of itself can be annoying. There are other kinds of problems that could arise here. So let's look at this example. What if I ask you to do e to the x cosine x? So first, doesn't look like a basic rule. Substitution, I don't even know what we'd substitute here, so I probably wouldn't think of that. So integration by parts is the only other thing we know about, so we'd probably try to use that. Notice here we have an exponential, here we have a trig function. Who gets to be the u? Well, okay, so start out by setting u to be cosine, or dv to be e to the x dx. Our du would be derivative of cosine is minus sine of x. Integral here is e to the x. So I plug that in. So here we have e to the x cosine of x equals to u times v minus the integral of v du. Here's a negative sign, that's going to turn that to a positive sign. And we end up with that. How do we continue? How do we deal with this integral? E to the x times sine x. It's another integration by parts. U equals sine x. Du would be derivative of that, which is cosine x dx. Our dv would be equal to e to the x dx. Our v would be equal to e to the x. And so we can say this integral is equal to e to the x cosine x plus, now we're going to put that, technically you could open a parentheses here, but there's a plus sign, so it's not going to matter. U times v minus the integral of v du. Okay, now what? Huh?
Will it just keep looping?
Yeah, and now we just keep going on forever and ever. Just keep, let's do it again. Obviously something's amiss here. This integral is, that's the guy we started with. So now you can kind of see, well, if I were to like do this again, I'm just going to end up where I started. How to actually get out of this infinite loop that we seem to be caught in.
Can you add plus integral ex sine x dx each side?
Yeah, algebra is the answer. Right? There's no more calculus because now this thing, now I have an equation where I want to solve for this thing. So how would you do that? Group like terms. Bring it to one side, isolate it. So at this point, so here's a situation that could end up with by parts as well. Sometimes you're doing integration by parts and what you realize is after a few iterations, you actually end up with the original guy. Now when you do that, you just stop and just solve for it as in an algebraic equation, right? So it's kind of like if you had x equals a minus x, how would you solve for x? Well, you move the x to the other side, divide by 2. So that's what we can do here. Can move this to that side. I'd have 2 of these integrals on that side, then divide by 2. So if I move this guy over here, of course there's going to be a plus c when it's all said and done, and then I would just divide both sides by 2. So I end up with 1/2 times all of this. When you're finding an indefinite integral, there's always a plus c. Right, this integral has a plus c associated with it. There's always an arbitrary constant of integration, as long as you don't have numbers on the thing. So that would be the answer. That's another kind of situation that you can come up with. So integration by parts, it can get a relatively easy problem where you just do the formula once and you get your answer. The integral that you end up with is super easy, you can deal with. Sometimes the integral that you end up with, you have to do with some other technique like substitution or something else. Sometimes you have to repeatedly use integration by parts to break down a function into simpler and simpler versions until you can finally just do the last integral. Sometimes you can do integration by parts and you end up in kind of a loop, in which case stop the loop once you get the original and just solve for it as in an algebraic equation. So there are a lot of situations that can arise here, and many of them could be quite annoying. So let's actually look at a way to actually do integration by parts, but without actually looking at the formula like that. And ultimately, I'm going to show you that it can deal with all these situations that we encounter, and there's a technique called tabular integration. Which is a pretty cool method. And now you guys are in the know, because when I was doing Calc 2, I never learned this method until like after I graduated. I had a bachelor's degree before I saw this, and I'm like, why did no one tell me about this? And it's funny, I was being observed earlier by one of the senior members in the department, and he's like, I didn't even know that existed. It's like, so he found out about that today, but I'm telling you guys early. You heard it here first. Tabular integration. It's pretty much a very systematic way of doing integration by parts without actually having to memorize the formula, really. Basically, you memorize the algorithm of how you would set up the table, right? That's the root word, tabular table. Okay. So, just another way to do integration by parts, and it makes a lot of the situations a lot easier. So, for example, we're going to do the x to the 5th times e to the x integral of that with this method, and you're going to see and hopefully appreciate how much quicker it is than actually doing it with the formula. So here's how the algorithm actually works. So it's pretty much an algorithm. I'm going to tell you what the algorithm looks like, and then I'm going to tell you how to actually apply the algorithm. So let's say you have an integral, and it's a product of functions, so you know you want to use int by parts. So let's say there's an f, and there's an uppercase G dx. And I'm specifically thinking of the x as the guy who's going to be the u, and the G dx as the guy who's going to be the dv. What you can do is you can set up a table. And so right below the integral, you start setting up a table, 2 columns. Now remember, the u guy is the guy you're going to differentiate, right? So you do that, you just keep differentiating. So that's the first derivative, that's the second derivative, and you keep going until you get to the nth derivative. I'm going to tell you how to know when to stop. What does your n have to be for your particular situation? Okay? So you're just going to differentiate something n times. I'll tell you how you know what the n has to be, right? So you keep differentiating the u. In this column, you're going to keep integrating the g. So let me, I don't really know of a nice shorthand notation for that. Let me put a subscript. So that's the first antiderivative. Then take the antiderivative of that, second antiderivative, keep going, I will get until I get to the nth antiderivative. Okay? So you set up the table with the u and the dv, keep differentiating, keep integrating until you get to the opportune moment. I'll tell you how to know the opportune moment. Okay? But as far as that goes, what you will now do is you are going to be multiplying in a diagonal. So I'm going to take the f times that guy. And I'm going to take this times that. And I'm going to take this times that, and so on and so forth. Right? So I'm going to keep multiplying across the diagonals. Once I get to the last step, I'm going to multiply across here. There is also a sign change that goes along with this. So the first one takes a positive sign. The next multiplication will take a negative sign. The next one will take a positive sign. The signs alternate. So here you would, depending on what step you're on, you would have a plus or minus. And then here, based on that, you'd have a plus or minus. But the signs always alternate. Right? Now, if this guy's the dv, one integral would give you the v. So notice here what you're doing is actually the u times v, right? But then you keep repeating this. The sign change happens because there's a negative sign in the integration by parts formula. So once you start setting up parentheses, the negative is going to distribute and change all the signs. So that's what causes the alternating sign. Now, ultimately, once you set up this table, you stop it at the right moment and you do all these multiplications, the answer is going to look like the following. It's going to look like these products. So it's going to be plus the f times the g1 minus f prime times g2 plus f double prime times g3 minus dot dot dot. You keep going until you get to f n minus 1 times g. That's going to be plus or minus. And then you're going to multiply across. That's the fn times the gn. And for the last one, you actually take the integral of that. So that's like the ending of the integration by parts formula. And this has the same effect as nesting those parentheses. Now let me tell you, how do you know when to stop? You stop when one of three things are achieved. Okay, so first situation, how do you know when to stop? When the derivative, the nth derivative of your u is equal to 0. That would be one way to stop, to know when you're going to stop. So for example, if your u happens to be a polynomial, eventually it's going to hit 0, right? So if you add an x to the fifth, it's going to break down to an x fourth, x cubed, x squared, x constant, 0. It'll eventually hit 0, that's when you stop. So that will be how to know how large your table has to be. So that's one possible situation. Either once you keep differentiating, you'll eventually hit 0. Once, if that happens, stop. Or another situation that can happen is when the fn times gn is the original integral. So this is when you have that revolving situation where you kind of get the original back. Eventually you'll see the original staring at you right in the face and you'll know to stop. Or the third scenario when you would stop is when you notice this guy is maybe we should put that in quotations, easily integrable. By other methods. right? So you'll eventually get to a line where you can see, you know what, that's actually pretty easy to do by substitution. Or that's pretty easy to do just using the power rule, or, right? So you keep going until you hit one of these three scenarios. Either the thing you're differentiating would eventually hit 0, or you'll see there's going to be a row that looks exactly like the original integral, or there's going to be a row that if you multiply across, it's actually super easy to deal with without needing integration by parts. And then you break the loop, and you stop, and then you do this mechanism over here, and that is actually your integral. So copy that down, and I'll do an example. Right. Well, I'll do examples to illustrate all three of these situations. Looks like everyone's done copying. So let's actually do that guy that you asked you to look at last class. Now you can imagine, hopefully, or you don't have to imagine, you can try it afterwards. Try using the formula 5 times in a row, and then see how you like it, and then you can compare it to what I'm going to show you now. So here we have an integral x to the 5th times e to the x. So I'm going to set up a table. And I can see, hey, that guy's a polynomial. Eventually, if I keep differentiating, it's going to hit 0. So I just do that. Derivative, 5x to the 4th. Next derivative would be 20x cubed. Next derivative would be 60x squared. Next derivative would be 120x. Next derivative would be 120. Next derivative would be 0. Stop. So once you see 0, you stop. So that's one situation. I hit 0. So what I'm going to do now is I'm going to integrate. So integral of e to, this one's easy. This is just, you keep integrating to get e to the x back over and over and over again. And now we're going to multiply along the diagonals. So this would take, the first one is a plus sign, minus sign, plus sign, minus sign, plus sign, minus sign, plus sign. So what this guy ends up looking like is this times this, x to the 5th times e to the x, minus 5x to the 4th e to the x, plus 20x cubed e to the x, minus 60x squared e to the x, plus 120x e to the x, minus 120 e to the x, plus, now this is the last leg, that's the integral of 0 dx. Now obviously the integral of 0 is going to be a constant, so this is where our plus c would just come into play. So that's just plus c. And that's actually the answer. Simplify it a little bit, e to the x is a common term. So it's just e to the x times x to the 5th minus 5x to the 4th plus 20x cubed minus 60x squared plus 120x minus 120 plus c. You're very welcome to try the previous method that we did last week to get to that answer. You'll have to apply the formula 5 times in a row, expand all the parentheses, recombine, but eventually you'll get here. So this is what's known as tabular integration. Integrate in a table as an alternative to applying the integration by parts formula directly. And this is the first kind of scenario. What you're differentiating eventually hits 0. So that's typically when your u is going to be some sort of polynomial. As an illustration of the second situation, let's actually redo the guy that we had earlier. Now, I want the u on the left, so we'd rewrite that as, say, cosine of x times e to the x. I'm going to set up this table. Now, the thing is, I can anticipate what's going to happen because e to the x keeps being itself. Cosine of x will eventually come back to cosine of x once you differentiate twice. First order is going to get us a sine x, the second is going to get us cosine x again. So I'll keep differentiating, differentiate this, minus sine x, integrate that, e to the x. Differentiate this, minus cosine x, integrate that, e to the x. Notice here on this row, that is the original guy. So that's situation 2. Once I get to the original, here's where I stop. And now I start doing that multiplication along the diagonals and then back here. That's going to be a plus sign, this is going to be a minus sign, that's going to be a plus sign. So what ends up happening is this integral would become positive e to the x times cosine of x. It's negative sine x times a negative makes it a positive times e to the x. And going across here, it's positive e to the x times a negative cosine of x. And on the last one, you integrate. Now at this point you notice that, okay, once you get the original is when you stop and you just solve it as in like an algebraic equation. Something that people often do is they'd say set this integral to be I. And then once they see this they realize, oh, that's just I again. And so from here they can say, well, I is equal to e to the x cosine of x plus e to the x sine of x. Minus I, bring the I to the other side, 2 i's equals. And then you divide both sides by 2. And so you get the answer that way. So tabular integration can also deal with the situation where an integral revolves on itself. Right? Just stop in the row where you see the original integral appear again. And then solve for it like algebra. Right, as you would in an algebraic equation. To illustrate the third situation, also want to do an integral that we've already done so you can actually compare. We looked at this guy last time. Now according to Liate, our ln x would be the u. So to set it up for tabular integration, I want that guy to be on the left side. We set up the table. Differentiating this, I get 1 over x. Integrate that, I get x cubed over 3. At this point I can appreciate a couple things. One, this will never hit 0. Because if I start differentiating that, I'm going to get a 1 over x squared, and then there's going to be a constant times 1 over x cubed, and etc. This is just going to go to x to the minus n. It'll never actually hit 0. However, right away I can see in this row, if I were to just multiply across here, I get x squared, which is something I can do with the power rule. So I would stop after just one step here. So I multiply this, positive, multiply that with the negative sign. And so this integral would be ln x times that minus the integral of this times that. So that just becomes x cubed over 3 ln x minus 1/3 x squared dx, which now just becomes x cubed over 3 ln x minus x cubed over 9. And that's the same answer we got last time. So this was just one step, and as you look back in your notes, you'll see that it only took one application of the formula to actually figure this one out. So that's what your table only has really one row, one additional row. So yeah, those are the situations. You can do tabular integration. You stop either when you see a 0, or you see the original integral popping up, or you realize that if I multiply across the row, that's actually pretty easy to deal with. So yeah, that's tabular integration. It's a nice technique, and it helps us when integration by parts can get pretty annoying or repetitive or whatever. Or as you can see from this example, you can actually completely replace integration by parts with tabular integration. It can deal with every situation that integration by parts can deal with. Even the ones where it's kind of silly, you only have to apply the formula one time, it can still deal with that situation. Yes?
Is there anything that you can do with it?
No. It will work whenever integration by parts works. So it's pretty much writing integration by parts in more of an algorithmic kind of way. Right? So if you wanted, for example, to program a computer to do integration by parts, you'd probably program it with something like this, as opposed to telling it, oh, just apply this formula over and over. The computer's going to like, what do you mean? You know, what do you mean by just apply the formula over and over? Okay, construct this table, multiply these cells here, and then do calculus in this way, and then. So it's pretty much replacing integration by parts. Sometimes I personally use just a mix and match. So if it's something easy like this, I'll just do integration by parts like the regular way. But if it's something like x to the 5th times e to the x, I'll do tabular. But you can do either or you can only do this one or only the other one. Yeah, kind of figure out what you like. So in terms of new material, that's pretty much it. Let's actually do some more examples here. I'll give you guys a chance to set some of these up, and then we'll knock them out. Okay, so. Try those. I'll give you guys about 5 minutes to at least set them up. Tell me what your first step would be. If you do by parts, what would the parts be? Once you figure out the first step, we will go through the problem completely. See what will happen. But with these integrals, half the battle is just figuring out what is the first step. What method am I going to use? What would the first step look like? Once you do that, you're able to follow your nose through the rest of the problem, at least at this level. So actually try setting those up. Again, A. How would you do A? Yeah? Regular substitution. U equals x cubed. du would be 3x squared dx. dx would be du over 3x squared. We plug these in. X squares cancel. So you have 1/3 integral of e to the u du. Integral of that is e to the u. That's your answer. No integration by parts. That was just. Trick question. But not really. You always try to get away with the easiest thing first. So, yes, we're doing integration by parts in today's class, but every time you look at an integral, you always check, does the basic rule work first? Does substitution work? If not, then you think integration by parts or something harder. This one, regular substitution takes care of this. It's not, we don't need integration by parts. What about this one? Yeah? You did by parts. What were your parts?
U equals x, v equals tan inverse. No, arctan dx. And then du will be dx and v will be whatever.
U equals what? Well, I mean, arctan x. This is one function here. Arctan of x. The x isn't separate. Like, you can't have tan inverse by itself. It has to be tan inverse of something.
And then one will be.
So we definitely don't know how to integrate tan inverse, so that has to be our u. And our dv would be chosen to be 1 dx, right? So this was like, we did a similar one to this, where we looked at sine inverse of x. Just pretend that there's a 1 here. And so here you have an inverse trig, here you have an algebraic. So your inverse trig gets to be the u. Our du, what's the derivative of tan inverse of x? Yeah?
1 over 1 plus x squared.
1 over 1 plus x squared. And the integral of 1 is just x. So now I would plug this in. U times v minus the integral of v du. How would you do with this integral? Substitution. What would you substitute? Right. U equals 1 plus x squared. Your du is going to give you the 2x dx. You're going to factor out a half. Ultimately, you get 1/2 ln 1 plus x squared. So with this guy, I just did regular substitution. U equals 1 plus x squared. Details left to the reader. C. So e to the x squared has no antiderivative, but it turns out e to the radical x actually does, believe it or not. In fact, the nth root, e to the nth root of x will have an antiderivative, but the larger n is, the more annoying it gets. The trick here is actually to start out with a substitution, and I'm going to do a t substitution. T equals radical x. This means that my dt will be 1 over 2 radical x dx. In other words, my dx would be 2 radical x dt. Now remember, one of the things with substitution is the derivative of the thing should be present in the original function. You might notice that 1 over radical x is not present in our original function. However, we can be the sneaky mathematicians that we've been all semester and kind of sneak something in there that wasn't there before by simply multiplying and dividing. There's one way to get it in there. So I get that 1 over radical x, and then I can replace the top radical x with t. Another way to get to this situation is to realize that I could actually square both sides, then do the derivative of both sides, and my dx will be 2t dt, and that you'll get that t back anyway, which I can do right now. Radical x is t, so here I can just replace this with 2t dt. So now this integral actually becomes, after applying substitution, 2t dt would replace dx. Then I would have e to the radical x, which is just e to the t. And so now I end up with this integral. That one is, of course, integration by parts. We've seen it a couple times. So here I choose u equals t, dv equals e to the t. Ultimately, we can go through the motions. We've done this a couple times by now. So we know the answer should be t e to the t minus e to the t. So this is 2 times radical x e to the radical x minus e to the radical x plus c. That's our answer. Kind of a strange one, but so another one where we start out with a substitution. This was kind of the opposite of one of the previous examples. Here we started out with a substitution, but we ended up with something that needed by parts. So once you learn all these techniques, at any given time you can mix and match them as appropriate. So that this one, the trick here is also to start out looking with a substitution kind of thing. First thing you need to realize is that that x cubed can be written as x squared times x. So now you can notice, if I let u be this guy, my du is going to be that guy. And of course this guy would also, by that definition, be u. But of course, then you'd notice that you'd end up with an integration by parts situation, so you don't want to mix up the u's in substitution with the u in integration by parts, so let this be t. That will also be t, this will be dt. So I'll start out with t equals x squared. My dt would be 2x dx. So I would have 1/2 dt. Of course I've had it. We like to solve for dx. Is that, so you would plug it in, so you'd have x squared times x e to the t times dt over 2x. This x would cancel that x. This x squared would become t. And so ultimately, come all the way over here. We would end up with 1/2 times, well, t e to the t. Seen this a couple times now. This is going to be t e to the t minus e to the t. And in this case, my t is actually x squared. That answer. So as far as Calc 1 goes, these last, well, the last 3 integrals I did anyway, will pretty much be the most difficult kind of integrals you'll get in the entire course. If you figure out those guys, you're in pretty good shape. But yeah, as long as you remember, try to get away with the simplest thing you can at first, and only get more complicated when you have to. Doing a lot of practice so you start to see what the first step should be, and that'll put you in pretty good shape. I'll stop there for now.